Uh, I guess I was partly involved in the organization of this wonderful meeting, but I know firsthand how much work Abhishek and Rajesh put in. So thank you very much for putting together a really memorable event. Okay, so let me get started then. Right. So we heard Bhaskaran's wonderful lecture yesterday on the history of quantum mechanics, especially the work of Bose. And remarkably, it perfectly coincides my planned introduction, so I won't need to say much more about this. Right, so Bose introduced the idea of indistinguishable particles and how purely from statistics of indistinguishable particles, where you allow particles to occupy the same state, gave us Planck distribution function. And then Einstein extended that for massive particles to phenomena of Bose-Einstein condensation. And then in 1927, which came later, Sommerfeld started talking about many particle physics, which are fermions. And his work is really the foundation of modern solid-state physics, starting from the assumptions that electrons are nearly free particles that obey Fermi statistics. And that's really the central fact behind just about everything in condensed matter physics before, let's say, 1980s. Another big advance, which was in the same line of thinking, was the BCS theory of superconductivity, where they realized, at least in modern terms, as we'd say, that superconductivity is, again, an example of Bose-Einstein condensation, where the bosons are not elementary particles, but pairs of electrons. Okay, so today, so my talk today is to go beyond these foundations. There's been a dramatic change in the structure of condensed matter physics, say starting in the 1980s. And it's a study of quantum matter where there are many emergent phenomena related in particular to quantum entanglement. And these new emergent phenomena are crucial to understanding modern quantum materials, such as the high temperature superconductors, and have also surprisingly had quite an impact, I believe, in work on the quantum properties of black holes. All right. Okay, so this is a rough outline of all the things I want to go through. I'll talk about the more basic things slowly, and you'll forgive me if I review some things very quickly. It's mainly to give you an impressionistic picture of all the things that have happened. So the first part is about spin liquids. So these are, in today's language, you would say systems that can be approximately described as a collection of interacting qubits. So the qubits don't actually move, so they're bosonic degrees of freedom, and these can be realized in many, not only in quantum simulation devices, but also in many quantum materials. So I'll talk about two classes of spin liquids, those with an energy gap, those without an energy gap, and summarize some recent experiments. Quite amazingly, just in the last 2 or 3 years, as you'll see, there's been remarkable progress. This is an old subject, but it's really come to life in the last few years with some really impressive progress. The second part is more about fermions. What happens when fermions move around and start to entangle with each other. And a basic model that's taught us a significant amount is the SYK model. And I'll talk about some of its properties and its connection to various forms of quantum matter, and if time permits, also to black holes. So let me begin with spin liquids. Okay, so we'll talk about spin liquids with an energy gap, the simplest kind. And really the key idea here is the idea of resonance, and that goes back to, according to Wikipedia, Kekule's spooky dream of a snake eating its own tail. That was how he came up with the idea of resonance in benzene, where benzene consists of 2 different configurations of double bonds. And today we'd say that's entanglement of 6 electrons. So the same idea now we want to extend to quantum matter with infinite number of electrons. And that was done by Phil Anderson in the 70s in the context of a model like this. This is an antiferromagnet. These are qubits or spinor halves sitting on the vertices of a triangular lattice. And if they have a nearest neighbor antiferromagnetic interaction, then we know today that the ground state is this ordered state with the spins polarized along definite directions to optimize this ground state energy. This is the same configuration you would get if you treated the spins as classical particles. However, Anderson proposed that perhaps the spins would form singlets, just like a double bond in benzene, and these singlets would resonate with each other. So now there's really an exponentially large number of singlet configurations, and this superposition of all these configurations is described by the state over here. The ground state is a superposition of different dimer coverings, and all the information really is in these coefficients, C sub d. They have a certain rigidity that we now understand quite well, and that determines not only the properties of the ground state, but also its excitations. So in particular, what is the key new idea introduced by spin liquids? One way to say it is fractionalization, that if you look at excitations above this ground state, they look like particles locally, but they can't be created by any local operators. So you can't just flip a spin or eject an electron or something like that and create a single excitations. So it requires a non-local structure to create them. And another way to say it in modern language, there are different super selection sectors in the Hilbert space of an infinite system. And there's no local operation that can take you from one sector to the next sector. And this division of the Hilbert space into super selection sectors is a direct consequence of the long-range entanglement. So in terms of a mathematical theory, this was formulated is what's now called the Z2 spin liquid, where you can think of it as the deconfined phase of a Z2 gauge theory. So Z2 gauge theory is like electromagnetism, which is a U1 gauge theory, except the gauge transformations are only signs and not a phase factor. So it's very much like gauge theory that was studied in particle physics in earlier years. Okay, so for the RVB state in the Z2 gauge theory, there's a bunch of excitations or anyons or super selection sectors. We call them two types of spin-ons, as I'll show you what they are, and a Vizon. And these super selection, this whole structure coincide with what mathematicians now call an example of a unitary modular tensor category, and it's the same as in the toric code. So, sorry, I'm getting used to this. Okay. All right, so what are these excitations? So here's the ground state with long-range entanglement. So if I just flip a spin, I'm going to create a spin one object here. But now what can happen is that these two spin ones can move far apart from each other. And these individual particles are the fractionalized particle. They carry spin a half, and they also carry a Z2 gauge charge. A more subtle object is what you'd call the Vizon. And this is created by changing, very in a subtle way, these phase factors, these coefficients here in the dimer covering. Okay, so what you do is you pick a point, this point here, which is where the Vizon will sit. And then you take an arbitrary branch cut that goes from the point out to infinity. And then every time there's a dimer that crosses this branch cut, then you put in a factor of -1 in the superposition. So that's a simple variational ansatz for this excitation, which carries a finite energy above the ground state. So, as you look at different configurations, -1, and now you're going to get two of them crossing, so you get a +1. And it turns out that all of the extra energy is really only over here. The branch cut is invisible. It's a gauge artifact. And this localized excitations, however, cannot be created by any local operation. It requires you to really construct the branch cut and flip the signs all the way across to create one of these fractionalized particles. Okay. All right. So that's the simplest example of a Z2 spin liquid, of a gapped spin liquid, and I've given you a fairly explicit construction of how it's set up. Of course, we have today a fairly complete theory of its properties. And as I mentioned earlier, it's written in terms of a Z2 gauge theory with many other excitations coupled to it. There are many other gapped spin liquids that have since been understood very well. In fact, the earliest one, before the Z2 spin liquid was understood, is the Kalmar-Laughlin-Carl spin liquid. In this case, they were making an analogy with the fractional quantum Hall state. And Kalmar and Laughlin argued that you could think of a spin-1/2 system on the triangular lattice as a bunch of bosons in a fictitious magnetic field at filling fraction nu = 1/2. So this requires absence of time reversal symmetry, just like in the fractional quantum Hall states. It has a different unitary modular tensor category characterizing it. And I think Senthil will say much more about such states. Another important state that's been the focus of much theoretical and experimental attention is Ketev's state on the honeycomb lattice. So this is realized by having XX, YY, and ZZ interactions in the 3 directions. And then it turns out that in this case, there's a Z2 spin liquid in which the epsilon fermions, the spin-ons, have the spectrum of massless relativistic Majoranas. And then if you turn on a perturbation, then these Majoranas acquire a gap, and you get a Chern number in the band structure, and that eventually leads to non-abelian statistics. Okay, so I'm not going to say more about this, but there's a huge amount of literature on this, and even possible realization in quantum matter. Okay. So now let me turn to a more complicated class of spin liquids, which turn out to be much more common in quantum matter anyway. So these are spin liquids without an energy gap. And one of the first places they appear is in discussion of the square lattice. Now the square lattice, of course, what motivated all this interest in spin liquids in the 90s, starting from their possible relevance to the high temperature superconductors, which is made up of square lattice of spin-1/2s when you're in the parent insulating compound. So here are not completely updated results on numerical studies on this Hamiltonian with nearest neighbor and second neighbor interactions. So when the second neighbor interaction is weak, when J2 is small, you get this very familiar nail state, which is what's observed in lanthanum copper oxide, for example. Now, in the real world, in lanthanum copper oxide, you put in charge carriers, and that introduces many additional pieces of physics. But the motivation here is let's study a simpler model where we just turn on a second neighbor interaction and see what happens. So what happens is that in the square lattice, you go from this nail state to this valence bond solid state, where the singlets crystallize in, say, this columnar arrangement. So this is a state that has local entanglement between these two pairs, but nothing long range. It doesn't have any of the superselection sectors that I mentioned. So it's not strictly speaking a spin liquid. But there's been an enormous amount of attention over the past almost 30 years trying to understand how you go from this state to that. And there's a lot of numerical evidence that there's some nearly gapless spin liquid at the boundary, about which I'll say much more in the subsequent slides. Okay, so how do we make theories of such liquids? So the main tool here, which has been very powerful, is the parton method. So you take your spins, which are themselves spin-1 objects, and you write them in terms of these partons In this case, they're bosons, which carry spin 1/2. So the Hilbert space of these bosons is, of course, much bigger. But if you impose the constraint that there's exactly one boson for S equals 1/2 on each side, then you get an identical Hilbert space. And then you get if you substitute this in here, you get some complicated many boson interacting system, which you now have to study. So that's been studied a lot. And what invariably happens is that when you take the low energy limit, you get a gauge theory. So this is, as I mentioned, very much like electromagnetism or quantum chromodynamics. In this case, it's a U1 gauge theory. And this gauge theory is coupled to matter fields. And in this case, the matter fields are basically these underlying bosons. So they call them Z alpha. And you get a theory then, which at low energies has a relativistic form. So this is a theory which in very similar form has been studied a lot in the particle theory literature. You have a particle, a bosonic relativistic particle Z, carrying a U1 gauge charge, and it's coupled to U1 electromagnetism. But there are some subtle differences from ordinary electromagnetism. One important difference is that this is what's called a compact U1 gauge theory, which implies that there are monopoles present. And those monopoles, in fact, have not extremely heavy monopoles like in grand unified theories, but quite light. So if you now take this theory, U1 gauge theory plus monopoles, then you get this phase diagram. If these bosons condense, if the bosons undergo Bose-Einstein condensation, we reproduce this Néel state. And then if the bosons don't condense, then the consideration of monopoles showed that you have this kind of valence bond solid order, which is what's exactly seen in these numerical studies. Okay, so then the question becomes, okay, neither of these are really spin liquid, strictly speaking, but there seems to be, in a lot of the numerical work, as I already mentioned, some spin liquid-like state at the boundary with lots of very low energy excitations. So the understanding of that intermediate state actually requires quite a different formulation, which was introduced by, what's going on here? Sorry, okay, I'll just use that. By Affleck and Marston way back in 1988. So here the strategy is exactly the same. We write the spin in terms of partons, but these partons are fermions. And then you write down some mean field state. And in this case, the mean field state turns out to be fermions hopping with pi flux per plaquette. And then if you look at fluctuations, now it becomes a theory that was actually a very close cousin of what was mentioned yesterday for QCD. It's SU2 quantum chromodynamics in 2+1 dimension, not SU3 and 3+1. And there are NF equals 2 massless fermions. It literally is this relativistic theory in this Affleck-Marston mean field state. And I just want to mention here numerical work by Yassir Iqbal and others on precisely this model, which gave good evidence for the existence of state with these. These are the massless Dirac fermions showing up in their spectrum. But these fermions are coupled to this gauge field, so they're not gauge invariant objects. You have to take composites to detect them. Okay, but then you can ask, okay, here's some kind of gauge. The fermions look like they're nearly free, but they're not really. They're coupled to this quantum chromodynamic SU2 non-abelian gauge field. Now we know in quantum chromodynamics in 3+1 dimensions that that's a confining theory, that the theory confines, and in the end, the fermions don't remain massless. And that's exactly what seems to happen here. So you can study the confining state. And when you look at the confining state, lo and behold, they coincide with the confining states you obtained by using the bosonic parton representation. So that's a very important unifying principle. And it was taken further in beautiful work by various people here, especially Senthil, where they realized that there's sort of ultimately a triality. There's this theory of bosons, massless, nearly massless bosons coupled to U1 gauge field. There's this theory of NF of two Dirac fermions coupled to an SU2 gauge field. And then there's a third formulation, which is some kind of nonlinear sigma model with the Wess-Zumino-Witten term. And all of these are equally valid descriptions of these square lattice antiferromagnets for their spin liquid state. So it's kind of amazing that the most important model needed for understanding cuprates has this incredibly complicated structure, which has taken nearly 30 years to unravel. And now we have to connect this to experiments. Well, I'll say a bit about that in a few minutes. Okay, so this new formulation in terms of the nonlinear sigma model was used particularly in some beautiful work on the fuzzy sphere by Yinch and Hay and collaborators. And this really, their results supported this general picture, but found that in the end, if you didn't tune additional parameters, it seemed like there was always confinement. But it took a long time for this to happen, so there's a nearly critical gapless state. Okay. Then let's turn to the triangular and Kagome lattice. Here, Hastings and Wen proposed a very similar state, which is now QED rather than QCD, because it's a U1 gauge theory. And it's coupled to NF equals 4 massless fermions. So this is again a theory that's been studied in the particle physics literature, and it's unclear for NF equals to 4 whether it flows to a non-confining state, but it could well do that. And then you'll get a conformal, strongly coupled conformal field theory describing the antiferromagnet on the triangular and Kagome lattices. There's been an important advance on this in work by Song et al., where they looked at the effect of monopoles on this particular gapless U1 spin liquid and showed that, in fact, the simplest monopoles are not allowed. And so that enhances the possibility that this is actually present in triangular and Kagome lattices. And here again, there's very early on, it was work of Yasir Iqbal that showed some regime in the J1, J2 model of the presence of this NF equals 4 QED. Very important work, and recently has been this numerical study by Witek et al., who looked at the detailed spectrum of a triangular lattice antiferromagnet on a torus, and they looked at the whole set of excited states and found that essentially all of them map really very beautifully to this theory from NF equals 4 QED plus the allowed monopoles. However, there were still, if you read the paper carefully, there are a few states which are shown here that don't match this QED picture. Instead, they match what's called the quantum dimer model, indicating that, perhaps just like again in the real world for the weak interactions, we need some charge to Higgs field around, which will then take this to the physics of the quantum dimer model. And finally, let me mention this work by my former student, Henry Shackleton, who found a way to put this whole thing on a computer without a sign problem. In this case, you take a Z2 gauge theory of these S fields coupled to bosonic spin-ons. And the key ingredient here, which makes it quite different from theories that gauge theory that may have been examined, the lattice gauge theory results. This part of the action is the usual lattice gauge theory of matter fields coupled to a Z2 gauge field. But there's this factor here, which is the product of S's, the Z2 gauge field in the time direction. And that's the very phase having to do with the fact that you've got real matter, 1 qubit on every side of the lattice. And here you get all the 3 phases I mentioned, and there's possibly this QED theory, which is massless, is somewhere at the boundary of these phases. Okay, so you can see there's an incredibly rich structure that's emerged from just studying these very humble-looking spin models. and connections to really advanced and concepts in quantum field theory, and conformal field theory, and gauge theories. And but there's been a remarkable advances in the last 2 or 3 years even, and hopefully we are close to complete understanding. Okay, so now let me give you a quick survey of various experiments, all of which I think are just in the last couple of years, including one I will show, which was just released this week. So I'm quite excited about that. I'll get to that in a minute. Okay, so these are studies of the triangular lattice antiferromagnet. There's a whole series of them where you change the alkali atom, cesium, potassium, sodium. If you look at the sodium case, this is the neutron scattering spectrum shown here as a function of momentum in this direction and energy in that direction. And so you can also compute this. It was done here in the Schwinger boson theory. And there's a very good correspondence between this whole continuum of excitations you see at the high energies and the continuum of excitations you see here. However, at low energies, as this phase diagram shows, this thing acquires the 120-degree order I showed you earlier. And that also can emerge from this Schwinger boson theory. So here it seems, as the title says, ultimately it's ordered. But if you look at somewhat higher energies over here, you can't describe it in terms of the spin waves of the ordered state, but you really need these fractionalized spin-ons for an understanding of neutron scattering. Very recently, in the sodium analog of this compound, there it is. This is a paper still on the archive by the same group. They studied now this compound, which, as the phase diagram indicates, seems to be a spin liquid down to 0 temperature. And in this case, they observe an actual energy gap, which is required for this type of, what they claim is it's most likely a Z2 spin liquid, which does have an energy gap. It's very small, 23 millikelvin, but anyway, the evidence for it seems rather compelling. Okay, what else? Then there is another different compound, terbium, zinc, gallium oxide. Yeah, these look very frightening, but for the non-condensed matter people, all that matters is where the spins are. In this case, I believe they're on the terbium. And you just look at the terbium, and the terbium forms a nice triangular lattice. So you can model it by this J1, J2 model on the triangular lattice. And in this case, here's the observations. And these are numerical studies by these authors of the Dirac spectrum using the fermionic formulation. And they claim that in this case, there's really evidence for a gapless Dirac quantum spin liquid. Okay, next. Finally, one of the most interesting applications, just very recent too, is on what's called quantum spin ice. So this is a 3-dimensional configuration of spins, where they're sitting at the vertices of a tetrahedra. And there's some Ising interaction, which is dominant between the spins, and then also some S plus, S minus interactions. And there's various arguments that this kind of spin system should realize a U1 spin liquid. So now, since we're in 3 dimensions, the Coulomb phase, the ordinary Coulomb phase, is allowed, in contrast to the very complicated conformal gauge theories I was discussing earlier. And there now does seem to be evidence that there's an emergent electromagnetism in this system. So this is the low energy theory, where you get essentially a U1 gauge field. And this has both monopole and electric charge excitations. This should be called spin-ons. I don't know why they call them monopoles. And then there are also photons. So what's been seen so far, clearly, they claim, are the spin-on band and perhaps some indication of the low-lying excitations. And that's in this recent paper on, again, this complicated compound here, with cerium being the magnetic ion. So this is the neutron scattering as a function of energy at a certain point in the Brillouin zone. And this is the calculated spectrum, including both spin-ons and photons. So I guess the monopoles have not been seen, but they've seen the spin-ons and photons, and this seems really quite beautiful. Again, a very recent paper. Okay, so continuing on, let's go to the square lattice, which is the most interesting case. I should speed up. And the square lattice, there is a spin liquid that now seems to be seen, but on what's called the Shastri-Sutherland lattice here. So you have next neighbor interactions in this lower configuration symmetry, which is realized in this compound, strontium copper borate. So this particular antiferromagnet has an exact dimer ground state shown here that was in fact found by Shastri and Sutherland. But as you increase the value of J2, you get a transition which is very similar to that on the square lattice. You get a valence bond solid here and the Néel state. And in the vicinity of this transition, there seems to be evidence, as in this recent paper from NMR data here, of some kind of deconfined gauge theory describing the vicinity of the valence bond solid and then ordered state. All right. So now let me quickly mention the cuprates, which was really the reason for studying all these systems. So in the cuprates, if I take the normal state, there's 3 different regimes. And I will quickly mention what happens in the pseudo-gap metal. So if you go to the pseudo-gap metal, then if you do photo emission, you see a very strange looking part of a Fermi surface. And if you believe this as some sort of completed Fermi surface, then this Fermi surface violates a fundamental theorem of Sommerfeld's theory of electrons, which is that the volume enclosed by the Fermi surface does not equal the density of electrons. But there's been various self-consistent Green's function approaches from dynamical mean field theory that can model this type of spectrum. But one of the things we pointed out that if you have this kind of violation of the Luttinger volume, then there must be a background spin liquid. So this raises the question, where is this background spin liquid? So we pointed out recently that if you look at the literature, there's actually quite a bit of evidence that this spin liquid exists. This has come mostly from resonant inelastic X-ray scattering, where, for example, in this paper by Keimer's group, they talked about intense paramagnon excitations in the pseudo-gap metal. Some high energy spin excitations here that you study by Ricks. This is the old spectrum that was studied by neutron scattering at low energies. Now, they identified these as paramagnons, which are spin 1 excitations about a Fermi surface. But it's hard to imagine these are paramagnons because there is no large Fermi surface. There's only this tiny bit of Fermi surface I just showed you. So the most natural interpretation is that there are indeed spin-ons in high energies, as are required by the Fermi surface, similar to the high energy spin-ons that were claimed in this compound on the triangular lattice. And there's also this very nice observation, again by Ricks, by another group. And here in the ordered state, you get this very narrow spin wave excitations. But if you go into the doped state, you get this huge, this broad continuum. And it's hard to imagine this is a spin wave or a paramagnon, and a natural interpretation of this continuum that these are spin-ons. Okay. All right, so now another way of studying the pseudo-gap metal is in cold atom systems, and I think Emmanuel will say much more about this. Let me just mention that the theories we've been using have also been used to model these cold atom observations. All right, so moving on, now we take another set of systems in which there's been remarkable progress on realizing spin liquid-like states. These are the quantum simulators built of qubits in different ways. So this is a beautiful recent paper by Google of superconducting qubits that I think Pedram will say more about this afternoon. So I won't say anything more. And then another very important system is the Rydberg neutral atoms, which are trapped in optical tweezers. So basically what you have here is a ground state and a Rydberg state, which is very big. So when the system is in the ground state, the atoms don't feel each other. When it's in the Rydberg state, they feel each other by a very strong van der Waals interaction. And then there's the term here that, which is the laser, which can take you between the ground and excited states. So this is a model of bosons, hardcore bosons, which we had introduced some years back in a different context. And there's also what's called the PXP model, which is a special case, which is studied a great deal in recent years. So if you take this configuration and put it on different lattices, a lot of wonderful things can happen. And this is something that Ryan Samajdar played an important role in realizing, student here from Indian Institute of Science. And on the Kagame lattice, you can get very complicated looking phases, which are indeed observed in some of the experiments. So for this configuration of Kagame lattice, we were hoping that there's a Z2 spin liquid, but that was never very convincing. But then Rubin Verison and Ashwin Vishwanath pointed out, all you have to do is to put the atoms on the centers of the bonds of the Kagame lattice. That's the Ruby lattice, or the linked Kagame lattice. And then it turns out that, at least over a certain distance scale, you can think of the wave function as, again, an infinite superposition, very similar to the RVB state, where the big atoms are the Rydberg atoms, and the small circles are the ground states. And these Rydberg atoms try to avoid each other, and it's because of that that you end up getting this long-range entanglement. They don't have evidence for long-range entanglement, but there's at least local entanglement that they see quite clearly in the experiment. Finally, I just want to mention a paper to be in the archive very soon, where they take the Rydberg atoms on hexagonal lattice, like graphene. And now this is slightly different, somewhat different qubit configuration. And they're able to move these atoms around and apply XX, YY, and ZZ operations on the time evolution of the qubit. So there's a very ingenious technique of analyzing these atoms, and these are the steps. You create a Z2 spin liquid by active error correction, similar to what's done by Google with their superconducting qubits. And then you apply cyclic time evolution under XX, YY, and ZZ operators. And finally, they even measure the Chern number of the epsilon fermions and find that the Chern number is non-zero. So that's what's shown over here. They measure various string operators, and from that you can deduce that when you're in this regime here, you're in the non-abelian phase, which has a non-zero Chern number for the fermions. Okay. All right, so 10 minutes left, 12. Okay, so that was the first part of my talk. And as I can see, the summary is, spin liquids started coming alive in the 90s. That's when I started working on them. And there was quite a bit of progress then, and the field kind of faded away a little bit. But in the last 2 or 3 years, it's been amazing. I hope you get a glimpse of all the things that have been done. And I think the field is really coming to a mature point where we're really starting to understand what's going on. And one of the amazing things is that even these very, very simple models turn out to be remarkably subtle. Okay, so now let's talk about moving fermions. And as I mentioned earlier, it's Sommerfeld who first talked about moving fermions. And if you extend his theory, you find that the collision time of these electrons diverges as temperature goes to 0 as 1 over temperature squared. And then you can ask, what is the minimum possible time this tau could be for Sommerfeld's theory to be internally consistent? And you find that this time has to be bigger than what's now called the Planckian time, which is Planck's constant divided by temperature. And that's what's needed for the internal consistency of Sommerfeld's theory. And everything looks good because as temperature goes to 0, this becomes much longer than this, because there's 1 over t squared, there's 1 over t. And so low enough temperature, there's no reason to believe that Sommerfeld should fail. And that's what everyone assumed until the cuprates were studied, and in particular, the strange metal region now. And in the strange metal, here's a recent observation of the optical conductivity, which you measure the reflectivity and the transmission of a little piece of high temperature superconductor. And you find a scattering time, tau of omega, which is right at the Planckian bound, h bar over temperature, and also scales as a function of omega over temperature. So this is one of the more recent indication that this dramatic breakdown of the usual Sommerfeld quasi-particle description of metals in the cuprates. So, okay, so we need some solvable model to make progress. That's what I was thinking way back in '92. And so I decided to have a dream about snakes again. And you can think of this model, each snake represents an entanglement, so there's random entanglement between different locations. Okay, but here it is more specifically. You imagine how you have a bunch of sites, some fraction of which you occupy with fermions, and now you allow these fermions to move around, but you put a very important constraint that the fermions only move in pairs. So there's some amplitude, U11, 12, 5, 14, for the fermions to move from, say, 5, 11, and 12 to 5, 4, 14, and so on. So there's one such amplitude for any 4 choices of sites. And the main assumption you make is that all of these numbers are uncorrelated random numbers. That's really all you need. And you can solve this problem then in the large N limit. And also today, with the contribution of string theorists, an amazing amount has been understood, even at large but finite N. Okay, so there's the Hamiltonian, if you want to see it. This is the 4 fermion operator, and these random numbers, U alpha, beta, gamma, delta. So before describing its properties, let me connect to Michael Berry's talk yesterday, where he talked about the random matrix model. But let me formulate it in a many bodies way. So here's some random matrix, Tij, and the fermions hop one by one in this case, from between different sites with this random matrix. This is the random matrix model that Sommerfeld may have written down to describe a little quantum dot. Okay, so Michael told us about all the properties of the single particle eigenstates of Tij. So they're equally spaced roughly with a spacing about a 1 over n. And there's some density of states, which for the random matrix is a semicircular density of states. Now, since it's a many-body system, you fill up the first, if you have q times n particles, you fill up the first qn states. And then there's a sort of Fermi surface or a boundary between the occupied and unoccupied states. But the spacing between the states at the boundary is about a 1 over n. Now, what I want to think about this is a many electron system, not a single electron system. And for this, so what we look at then is the many body density of states. So here, the energy E is the sum of the energies of all the occupied states, N alpha, E alpha. So you have 2 to the n such states. And this is just a histogram of all the states for a simple random matrix. And if you look at a regime where the energy is extensive, then you can understand this behavior from thermodynamics. We know that one of Sommerfeld's important results was the entropy vanishes linear with temperature. And this translates for the density of states to a density of state which is exponential of the square root of n times the energy, just by the usual conversion from canonical to microcanonical ensemble. However, if you look at very low energies here, down to the ground state of the many-body system, the spacing between the energy levels becomes very sparse. Because what's happening here, the way you create a low-energy excitation is take an occupied state and move it to an empty state. And that will cost you energy 1 over n. So the density of states, therefore, at low energies is of order n. And the presence of this low energy, very sparse density of states at very low energy is a clear indication that there's a free particle description here. That's a quasi-particle description of this state. Okay, now you do the same thing for the SYK model, this model here. And now here's what the density of states look like. So if when the energy is extensive, you have the same behavior, well, almost the same behavior that you had in the free particle case. You have e to the square root of 2n gamma e. But now there's this exponentially large factor, e to the n s naught. And in terms of the entropy, this means that the 0 temperature limit of the entropy in the infinite n limit is non-zero. And if you look at the low energy density of states, there's no tail here, as you can see. It's still exponentially large. In fact, it has a square root edge, and it's exponentially large, e to the n s naught. And this is a immediate red flag. This is a system that has no quasi-particle description. That is, you can't go from one state to the other by adding and removing a few particles. You have to completely change the entire wave function. So there's really random complex entanglement among these many states, which are accidentally, and they have to be there, exponentially close to each other. Okay. So that's really one of the key properties of the SYK model. And there's also, through the efforts of string theorists, we know how you cross over from here to there. Okay, so to summarize this, another thing you can find when you analyze the SYK model and you define an appropriate scattering time by, say, looking at the analog of the optical conductivity, it has exactly the form that was obeyed in the optical experiments in the cuprates. So this is something we realized a while back and we got very excited about it. But then there's this annoying fact that the entropy doesn't vanish as temperature goes to 0. So you get a 0 temperature entropy without exponential ground state degeneracy. This is really the first model to exhibit this feature. And we were kind of disappointed by this because certainly the cuprates had no indication that there's such a large entropy at low temperatures. So that's why we put this result in the appendix of this paper and kind of put it aside for a while. All right. Okay, I move on. All right, but it turned out that this remarkable feature of the entropy is exactly what's needed to understand black holes, a certain class of black holes. So let me say a little bit about that. So black holes are solutions of Einstein's equation. There's a black hole at the center of our universe, center of our galaxy. And in fact, that matter collapses all the way to the center according to Einstein's equation. And so we need a quantum theory to understand what's really going on inside a black hole. However, the key feature where quantum entanglement starts to play a role is to go back to the classic EPR experiment and imagine you do this by putting one qubit inside a black hole and the other outside a black hole. They're still entangled, but as an observer on the outside, you have no access to the black hole inside. It's out of your observable universe. So to you, this is a random qubit. And this is a very simple way of understanding Hawking's and Bekenstein's fundamental result that black holes have a temperature and an entropy. Okay, so if the black holes have an entropy, a key question in quantum theory of black holes is what is the D of E? Where is the D of E? There's a formula for the entropy in Boltzmann's grave, and there's a formula for the entropy, well, the temperature really, on Hawking's grave. And are these graves compatible with each other? That's really one of the central problems in quantum theory of black holes. So what I pointed out in 2010, but there's certain features of black holes that look really exactly like the SYK model. One is that if you look at the ring down time or the quasi-normal mode damping time, which is computed by Vishveshvara before Hawking, when you express it in terms of the Hawking temperature, it's again this precise Planckian time that the SYK model exhibits. Secondly, if we take charged black holes, you take the 0 temperature limit, or also rotating neutral black holes, they again have this remarkable feature of having a non-zero 0 temperature entropy, which is given by the area of the black hole for that charge. So immediately, if you make this connection to SYK model, this tells you that this black hole Hawking entropy is not realized by an exponentially large ground state degeneracy, as is the case in using BPS states in supersymmetric computations. But it's really something like that happens from the quantum chaos of strongly entangled states, as in the SYK model. So anyway, this connection has gone remarkable advances, and since I'm out of time, this is the density of states of a charged black hole at low energies. This is the latest result. This is the Bekenstein-Hawking formula. The cinch is exactly what appears in the SYK model, but you can fix the coefficient right here. And then there's a very mysterious and much more subtle power law prefactor in the area of the black hole that was determined by Elyasiu, Murthy, and Turiachi. Okay, I'm all done. There's one more part very quickly. So that was connecting the SYK model as a quantum simulation of a black hole, or the inside of a black hole. To an outside observer, it's a charged black hole at low energies is very similar, essentially indistinguishable from an SYK model. But what about the original motivation, the strange metal exchange of the cuprates? We know we can't literally take the SYK model and map it there because the entropy doesn't match. So this is a direction there's been a huge amount of work in the last 10 years or so. And very recently, we proposed a modification of the SYK model, which sometimes called the two-dimensional Yukawa SYK model, where you have in addition a bosonic degree of freedom, which is describing a certain quantum phase transition, and you also have spatial randomness in the position of the quantum critical point. And in this model, we can actually capture both the entropy and the scattering time as measured in experiments, as we show here. So to recap the discussion, and the SYK model describes multi-particle quantum entanglement, resulting in essentially loss of identity of the particles. No low energy property tells you that there are actual quasi-particles present, although at high energy you can see them. And a modification of the SYK model has made some progress in understanding properties of the strange metal. And somewhat more remarkably, there's a dual formulation of the SYK model where it looks exactly like the low energy theory of charged and rotating black holes. So thank you.
Thank you, Subir, for a wonderful talk. I think we have time for a few questions.
Hello?
Yeah.
Yeah. So if I have understood you correctly, like the density of states of the SYK model can capture the features of this density of states of black hole, right?
Yes, so this is a picture of an SYK model, an actual calculation of DOE.
So assuming SYK model of the black hole, you have got this density, right?
Strictly speaking, you get this cinch factor. This prefactor is, well, you just do it's just a prefactor you get from the Hawking calculation.
So as I understand.
And this is not part of the SYK model. This factor of 347 over 90 is special to quantum theory of gravity. There's a different factor for the SYK model.
That's fine.
Okay.
I mean, my question is beyond this, that what about the fluctuations? Because SYK model for me is a random matrix model.
Well, hopefully I've convinced you it's not the usual random matrix model.
No, I don't
believe
it's
many body model.
Fully agree. But it is, for all practical purposes, it is still a stationary random matrix model, right? Wigner-Dyson model, ensemble?
Yeah, I guess it was introduced in nuclear physics, as I mentioned here on this slide. They called it the two-body random ensemble. It appeared in nuclear physics in the 80s, but they didn't get any of the results that I presented. There was just some numerical study.
Yeah, no, that's fine. I mean, no, my question is just like, I want
to
please,
understand. What's your question?
Yeah, see, whether you can capture the fluctuations also. Like the two things have the same fluctuations.
These results are consequence of all fluctuation. It's a full quantum theory. Nothing has been left out at low energy. It's exact.
The density, the spectral fluctuations I'm talking about.
Those, okay. So I'm looking at the coarse grain properties, but the coarse graining here is much better. So if you look at, the low energy states, of the usual one-body random matrix model, the energy level spacing is 1 over n. Okay, and everything Michael Berry talked about was the statistics of these spacings. Now it turns out that if you look at the statistics of these spacings here, that's also given by the Wigner-Dyson ensemble. But the important difference is now the level spacing is not 1 over n, it's e to the minus n. And to see that is a far more subtle thing. It's been shown by, effectively by Sachdev and Stanford by a theory of wormholes. So they have an explicit connection all the way from the SYK model. You start from the microscopic SYK model, and you go to this theory of wormholes, and then you get the random matrix statistics of these level spacing. Now, the point is, everything I've talked about, correct, is about the average density of states. I haven't discussed the statistics, but that has been worked out.
Subir, I'm sure you are aware of system-dependent random matrix ensembles, right?
Yeah, so
Sparse random matrix ensemble.
this peak here is a
Try that there.
Yeah, so this peak I don't believe applies to these black holes. This is system dependent. I was referring to the behavior down here, which is not system dependent.
Sumati?
Here.
Okay.
Another talk.
So what do you think would consider a smoking gun signature experimentally for spin liquid? Because most of the experiment you're talking were more focused on band structure.
Well, this is
From
not band
office.
structure, it's the continuum scattering.
Yes, yeah.
Yeah, well, I mean, I think,
What is liquid about it to be seen, you know?
well, so example, here's a plot. So in this case, you have a spin wave excitation, which is a very sharp line. So at each momentum, there's only one excitation. Whereas here, for each momentum, there's a whole continuum. And this is related to the fact that when a neutron comes in, it can't create just one spin-on. It has to create more than one. And so that's the essential property of a spin liquid, that its excitations are not created by a local operator. So this is fairly direct evidence. So now I would say, it depends on your standards, but if you can do a microscopic calculation and get quantitative agreement with some kind of neutron scattering like this, that's pretty good evidence. Well, for a mathematician, mathematically, you really have to take some quasi-particles and braid them and see a phase. That's, of course, much more precise, but we can't do that in quantum matter, mostly. So that's where you have an advantage in the quantum devices.
Naina.
Yeah.
So it was a really nice review of the spin liquid. So I just had a question. So all these spin models,
Yeah.
you were getting either fermionic or bosonic theories, and whether it was a matter of, to some extent, like there were some things where you were using fermions and some places bosons, and to what extent was it a matter of choice versus some fundamental reason behind it? And if it is the latter, can you tell a priori whether like what you're looking at is going to be fermionic or bosonic?
Yeah, that is the precise question that is at the heart of the field. Yes. The answer is, in some cases, yes, in the other cases, no. So for the square lattice, as best we understand it, as I showed this duality diagram, triality diagram, this one, it doesn't matter. They're actually dual to each other. There's a fermionic description here, there's a bosonic parton description, and if there was a conformal field theory, they are basically both realizable. So the difficulty here is that the real world is sitting in the center. You're doing an experiment. But we can compute in these limiting cases some things. And so, this is the challenge we face. And the strategy we've been following is, depending on what you're observing here, one of these other limiting cases may be the best starting point. So for some cases, you better use fermionic. For some observables, it's better to use fermionic. For others, it's better to use bosonic, depending on various details. So that's a strategy we found quite fruitful. But for the triangular lattice, like here, yeah. So this is the formulation in terms of bosonic spin-ons that Henry simulated. But it's just too complicated. I can't look at this model, especially because of this Berry phase term, and tell you what it's going to do. You just got to put it on a computer. And on a computer, you find the expected phases, but there's some kind of very strange gapless behavior going on, which we can't quite resolve. And it could well be that the only way to describe this region is using fermions. So, what the low energy theory here is probably, it could well be NF equals 4 QED. That has no known dual in bosonic variables, as far as I know. But these are strongly coupled theories. And even the concept of saying these are fermions is not very precise because ultimately the low energy theory is a conformal theory. There are no particles. Fermions is just a tool we use to do some perturbation theory. They're not really there. We can't observe them on their own. They don't have infinite lifetime because they're strongly coupled to gauge fields.
Thank you. So when a system has non-zero entropy at zero temperature,
Yes.
can you use it for something like a heat sink or for information storage? In this case
Well, there has been a proposal by Marco Pollini and others. Because of the large non-zero entropy, it has a very large thermal power. It also has a large particle-hole asymmetry. So you could use this for batteries and things like that someday. I can dream. I can start a company and then make a lot of money.
So to be, so partly response to Pradham's question there.
Yeah.
So in the first set of experiments that you showed, the potassium ytterbium cell.
Right.
So at least the schematic picture that you had looked like it was going from the 120-degree ordered state to Z2 spin liquid.
Yes, yes, correct. Here we go.
Right.
Yeah.
Now, as you may recall, you know, if this story is right,
Yeah.
then you should also expect soft fluctuations of the SI cross SJ order parameter.
Okay, yeah.
Right.
Okay, in the NF equals 4 theory.
No, there's just 120-degree order to the Z2.
Yeah, but as formulated in some NF equals 4 QED theory.
No.
Okay, fine, go ahead.
Yeah, so there's just
I've learned almost everything about this from Center, so please educate me.
So there is a very concrete prediction that comes from the theory that is a weird order parameter.
Yeah,
Which
okay.
is not ordered. It's not the primary order parameter of this phase.
Yeah,
Which will have slow correlations.
sure, right.
At basically the same power as the dominant spin correlation.
Yeah, good point. So in the same vein, if you just take this 120-degree ordered state, you expect low energy excitations, I think, at the K point. The fact that you see some low energy excitations here, even at the M point, there's the experiment, is again an indication that there's some fractionalization going on, similar to what you just mentioned.
The last question, maybe.
Yeah, I have a very silly question, so forgive me with. So in the SYK model, you have all particles that are just interacting with each other.
Yeah.
So in terms of entanglement monogamy, it would imply that the state itself is very weakly entangled, right?
I'm not sure. I mean,
Because if you have many particles and they're all entangled with each other, they can't really share high entanglement. So
well, I mean, so if you look at this, it's a little different from the Kekulé thing, but the particles aren't actually moving. They're just exchanging valence bonds. That's not what's happening here. So for example, you have a process where particle 11 can entangle with particle 12 to go to these sites. When this happens, they entangle with each other. On the other hand, particle 11 can also entangle with particle 8. All of that is happening in parallel, so to speak. So this is really moving fermions in a somewhat different way than the RVB type thing. Yeah. So I should say, in general remark, I mean, so I think really classifying and understanding many-body quantum entanglement is an incredibly complicated field, of which we only started to scratch the surface. And what I've described are two little islands. There's the SYK island and the spin liquid island, which are quite different from each other.
Let's thank Subir again for a very nice talk.